else. Yeah, it's my great pleasure to introduce to you Micah Corah. He recently joined as an assistant professor at the Colorado School of Mines. He is in the computer science department there, and he is focusing on aerial robots, active perception, and multi-robot teams. Before he joined Colorado School of Mines, he was at the Carnegie Mellon University as a postdoc in the AirLabs, and he also did his Ph.D. there. And I'm looking very much forward to, I'm pretty sure, very interesting talk on active perception for robot teams from visual search to videography. And that would be now yours, Micah, and you can also share your screen now.
Yeah, I'll get started on that.
So again, all seminar students, please turn on your camera. You will not count as being present if your camera is not turned on.
Can you see my screen right now?
Mm-hmm.
Thanks, Oliver, for the introduction. And thanks to everyone here for showing up. So as Oliver said, I'm Micah. I'm a new assistant professor in computer science at the Colorado School of Mines. And I'll be leading research there on aerial and mobile robots for tasks like videography, exploration, and inspection. I began this line of work while a postdoc in the AirLab at CMU, and I'm continuing it now at Mines. Previously, I did a postdoc at JPL, where I competed in the DARPA Subterranean Challenge, and I'll show you a little bit from that. And I did my PhD also at CMU with Professor Nathan Michael, where I focus mostly on robot exploration. This is an example from that. And talking about Mines, I should mention that we recently started a graduate program in robotics, and we have a growing number of faculty studying a wide variety of topics in robotics. So if you're interested in pursuing graduate studies in any of these areas, I'd encourage you to check us out. Now, back to the topic of today's talk. Today, I'd like to talk to you about my work on active perception for robots and teams of robots spanning from search and inspection to aerial videography. And as an introduction to my work, this video shows a team of robots exploring a sort of warehouse environment. These systems have a variety of uses, so you might envision a team of robots searching a disaster site for survivors and other signs of life as one example. Here, the robots are simply mapping a building by planning to maximize the amount of unobserved space they'll be covered by their camera views over the course of a few seconds. In general, perception planning, or you could say active perception, is an important topic throughout my work. So about a decade ago, micro aerial vehicles and aerial robots were curiosities of hobbyists and researchers, but now they're starting to embed themselves a little more securely in our media, in our industry. So a little over a year ago, Fox Sports began experimenting with a human-piloted first-person view drones in the USFL, which is a minor league American football organization. And as you can see in this video, this drone is able to capture the events of a play quite intimately and from angles that would not otherwise be possible. And looking at the picture below, we can see that decreasing size is one factor that enables safe deployment of these systems around players on the field. However, there's still only one or two drones to film many players, and this is with a team of highly skilled human pilots. Aerial robots are also becoming increasingly autonomous, as we can see for this Skydio drone. And actually, these shots are pretty close in dynamics and proximity to what you might expect from a human pilot. And this drone has quite good understanding of its environment. It can avoid obstacles and trees while still following the person being filmed. And it can also perform some maneuvers that be quite difficult for human pilots, such as how we now see it flying backwards in front of the bicyclist it's filming. Now, I apologize, this slide is going to be fairly US-centric. We can also look at the history of the development of innovative media technologies for team sports, such as American football. So in 1964, the instant replay systems that we now know well debuted. In 1984 was the year of the Skycam, which is a sort of cable-suspended robot. And this system is exciting because it brought television cameras onto the field during live play. Then in 2001, the iVision system was used during Super Bowl 35. This system consisted of a large number of pan-tilt cameras deployed around the perimeter of the stadium. And the thing that is really cool about the iVision system is that it allowed broadcasters to synthesize new camera views by interpolation, and that was all over 20 years ago. And as I already mentioned, manually piloted drones entered regular use in the USFL in 2022. So if we were to hypothesize about the future, I'd say that if we put these elements together, by about 2035, we might expect to see autonomous teams of drones that can film team sports from closer and more personal views while maintaining coverage over all important players. And we might even see the synthesis of new views via technologies such as neural radiance fields, much like as for the iVision system from 2001. And it's systems like this that I'm working toward in my research on multi-robot active perception systems. However, balancing the demands of filming, navigation, and autonomy is difficult for drones and for people. For example, this human pilot is doing a pretty good job of keeping a bicyclist in view, but they're not as good at keeping track of the environment and where they're going. And if you imagine expanding on this to multiple subjects being filmed, more drones, and more human pilots, the scenarios you envision may quickly become quite chaotic. So more generally, to build autonomous active perception systems, we'll have to overcome a number of challenges. Drones will need to understand their environments. This means being able to track, model, and detect the people or objects we want the drones to film. We need teams that coordinate and work together. For example, we may want several simultaneous views of one or more people. And meanwhile, we need to be able to manage risks such as involving collisions with other drones, with people, or with the environment. And last, any multi-robot system will be distributed to some degree, and we need to build systems and algorithms that are amenable to communication constraints and possibly unreliable communication. On the way toward building teams of autonomous aerial videography robots, I'm doing research in three main areas: aerial robots, multi-robot systems, and active perception. So regarding aerial robots, think of control, trajectory generation, and safe navigation. For multi-robot systems, planning and coordination, assignment and routing problems, and communication networks. And for active perception, think of optimizing camera views and maximizing information gain. And I like to think of active perception as something that makes my work a little unique. So I'll spend another minute introducing this topic. Active perception and active or informative sensing are collectively relevant to a wide variety of robotics problems and application domains. In this talk, I will start off by talking about exploring, or you could say autonomously mapping unknown environments. Then if we extend exploration to search and rescue tasks, as exhibited in the DARPA Subterranean challenge, we can also consider additional perception tasks, such as searching those unknown environments for objects that may indicate the locations of survivors. I'll also discuss target tracking and localization problems, where robots seek to estimate position or state of some number of subjects, say cars, people, or wildlife. And active perception is also relevant to aerial cinematography and reconstruction. And we can apply similar methods to maximize visual coverage and film groups of people, such as for filming team sports, as I've been talking about in the previous slides. More broadly, active perception and informative sensing methods are relevant whenever we want a robot to take actions to an observant object, operate in an unknown environment or estimate some unknown parameter, or even manipulate an unknown object. So as such, methods for active and interactive sensing and perception can be applied in creative ways and in non-traditional settings. For example, the figure on the left illustrates how a manipulator could recognize an object by feeling it and by planning tactile interactions. And on the right, I have an illustration from some of my earlier work as a PhD student. And here, a swarm of drones applies active sensing techniques by iteratively applying different forces to an object to estimate inertial parameters, while that object is on the ground before eventually lifting that object to safely engage in an aerial manipulation task. And now I'd like to get to the body of this talk, which I'll break up into two parts. For the first part, I will talk about exploration of unknown environments. This will cover planning to explore and design of objectives seeking to maximize the amount of unknown space that robots will observe. And it'll motivate development of exploration systems with applications like search and rescue. The second part focuses more generally on coordinating teams of robots in active perception tasks. I'll focus on general algorithms that I work with in my research and new distributed algorithms that I proposed. And I'll discuss how these approaches maintain optimization guarantees. I'll discuss a few different applications, but I'll emphasize aerial videography and reconstruction. With all that said, I'd like to start discussing exploration systems. So robots that can explore unknown environments are important to applications like search and rescue, because disaster sites may be unsafe for responders and because response time is often critical. Right now, aerial robots and perception tasks are also becoming increasingly prominent in rescue efforts, and at the same time increasing in scope. So now I'd like to refer to a report on the response at the Surfside condo collapse in Florida by Professor Robin Murphy. In June 2021, rescuers flew more than 300 drone rescue missions through the duration of the response to this disaster. Many of these missions focused on autonomously tracking flight paths to produce detailed maps of the environment to show how it was changing from one day to another. However, the scope also increased to include locating, inspecting, and even retrieving objects in the structure and rubble. So some examples from the response include searching for survivors, reading license plates to identify residents, searching for pets, and documenting the presence of belongings in the rubble. So to summarize, the general trend for operation of aerial robots in disaster sites is progressing toward more frequent flights in closer proximity and with focus shifting toward individual objects and with generally increasing autonomy. Search and rescue scenarios were also the focus of the recent DARPA Subterranean challenge, and I competed briefly in this challenge while I was a postdoc at JPL. The basic focus of this competition was to deploy teams of robots to explore subterranean environments, generally in simulated search and rescue scenarios. And teams were scored for correctly localizing objects such as helmets, ropes, or mannequins. Toward this end, we deployed a heterogeneous team of aerial, ground, wheeled, and legged robots to explore the competition environment. And these robots were equipped with extensive sensor payloads, including LiDAR, RGBD cameras, thermal cameras, microphones, sensors for CO2 gas, and more. And robots generally communicated with a single operator via a mesh network. So robots were also able to drop additional radios in order to maintain connectivity deep within the competition course. In the following slides, I will talk about a somewhat simpler exploration scenario where the goal is just to map an unknown environment, nothing else. However, you can also envision more complex scenarios akin to the subterranean challenge that might combine exploration, search, and inspection. When I think of exploration, I like to think about how to rapidly explore and map unknown environments. At a high level, I'm interested in two aspects of this problem. First, we can design robots that quickly explore on their own. And here I've included an example from some of my work in collaboration with Kshitij Goa at CMU. And I'll generally focus on single robot exploration for this part of the talk. However, increasingly large teams of robots can also explore an environment more quickly if they're able to cooperate effectively. And I'll discuss multi-robot coordination in the second part of this presentation. So generally, I'll be talking today about individual and sometimes multiple aerial robots exploring unknown environments. And these robots will observe their surrounding environment with forward-facing depth cameras or LiDAR sensors, which we'll use to update 3D occupancy grid maps. Since I'll be focusing on planning, I will assume the robot's locations are known. And the goal of the exploration task will be to generate an approximately complete map of the environment in minimum time. And for our purpose, we'll say the exploration task is complete once we've reached a threshold on the explored volume. The approach to exploration planning I'll be talking about is based on receding horizon planning to produce fixed finite horizon trajectories that consist of sequences of concatenated motion primitives. And such planners will all optimize trajectories to maximize some reward, such as a notion of information gain or coverage of unknown space for observations or views along a planning horizon, as I've illustrated here. Additionally, in exploration problems, robots will obtain a reward for reducing distance to what I call informative views. This mimics methods for frontier-based exploration that focus on navigating toward frontiers. That is the boundary between unmapped space and mapped free space. Know that there are a number of methods for solving informative path planning problems such as these. We can take a sampling-based optimization approach and apply Monte Carlo tree search to plan for exploration in this talk. And once we put together the components of the planning approach I'm about to present, we'll be able to obtain behaviors like what we can see here. Specifically, this robot is executing a sort of spiraling motion to quickly and safely cover a large open space. And this is sort of intuitive or emergent behavior is what makes me really excited about this line of work. And two components of the system are really key to this kind of behavior. So first, we use a view-based reward in our local planning. This enables us to evaluate the utility of a wide variety of dynamic motions or sequences of motions. And we also have a library of motion primitives that is able to take advantage of this flexibility with motions designed to facilitate rapid exploration. And I'll describe both of these components in the following slides. So the first step to building a flexible and efficient exploration system and to obtain behaviors like what I showed on the last slide is to design an objective for the perception task that is some sort of view-based reward. For example, you may be interested in observing volumes of unknown space, inspecting surfaces, or some combination of those two. And you may choose to weight cells in the map differently depending on the goal of your perception task. However, objective design can be challenging even when we have clearly defined goals because observations of unknown environments are highly uncertain. And because the distribution over possible environments may be poorly defined or difficult to sample. So one option is to simplify our model somewhat. And a simple example of a perception objective is what I like to call optimistic volumetric coverage. So here with optimistic coverage, robots are awarded according to the volume of unknown space covered by their hypothetical future observations. If we ignore this uncertainty and we assume optimistically that all of the unknown space is empty. So that makes our problem a little bit easier. Alternatively, we can design objectives based on probabilistic models of the environment and our observations. So-called information theoretic objectives apply these probabilistic models and compute different forms and approximations of mutual information. In general, mutual information characterizes how much information an observation of one random variable will provide about another. So as I've written it here, the mutual information describes the expected reduction in uncertainty of the map of the environment after planned observations with the robot's camera or LiDAR sensors. What is great about information theoretic objectives is that we're often able to evaluate mutual information for individual range observations in closed form, such as from a LiDAR sensor or a depth camera. And specifically, we can do so for discretized environments with independent occupancy probabilities, like occupancy grids or octomaps, if you're familiar, and with additive noise. So typically, we have Gaussian noise in the setting. The downside is that accurately evaluating mutual information for multiple range observations, multiple camera views, or multiple robots is a more challenging task. We generally have to approximate mutual information for observations involving multiple rays or views. So one way to do so is to compute a sum of exact values for nearly independent rays, like so. And while this approach is useful, approximating independence leads to some difficult trade-offs. And it is unclear how accurately this and other methods were able to approximate mutual information for multiple views, either along a trajectory or for observations by teams of robots. To address challenges for information-based methods, we can start by characterizing both coverage and information-based methods in terms of what I call expected weighted coverage. So here, consider the volume of unknown space a robot observes from a given camera view, and for a distribution over possible realizations of the environment, the unknown space, like I've shown here. The expected coverage is the expected volume of observed space given this distribution over possible environments. An exciting result from my work on this topic is that mutual information without noise fits the form of expected coverage. So in other words, this special case of mutual information is a kind of coverage objective. And this realization both enables efficient evaluation of the mutual information, and it's important to the analysis of the distributed multi-robot planner, which I'll discuss later on. Additionally, that optimistic coverage objective that significantly simplified our approach that I presented earlier is a special case of mutual information. So if we take the limit of the mutual information as the prior probability of occupancy in unknown space approaches zero, we can get an objective that is proportional to optimistic coverage. So what that means is that if you're exploring a space that's mostly empty compared to what you're able to see, then it might be reasonable to assume that the empty space is simply, or the unknown space is simply empty. I have some results comparing information theoretic and coverage-based methods. So here we compare the optimistic coverage objective I've been talking about to CSQMI, which is an information-based method for tent royals with a team of robots exploring the boxy environment shown on the right. And we found that the optimistic coverage objective provided a 16% improvement in completion time in these experiments, which is a positive false result, or positive first result here. And this potentially goes against intuition, as information-based methods are generally posed as being more advanced. However, the approximations I highlighted earlier are a potential cause for this difference in performance. So then once we have our view-based reward, the next step is to generate or optimize trajectories for robots to explore at high speeds. As I've already mentioned, we take a motion primitive approach, which means that we'll be optimizing sequences of more or less predefined trajectory components. Now I'd like you to take a step back and consider the different types of steady state behaviors that can occur while exploring the environment. So first, a robot may move along that is parallel to a frontier. In this case, the robot is planning to move through free space, and its speed is constrained only by the platform and design limits. However, the robot might also move toward a frontier, and in this case, it may encounter obstacles just past the maximum range of the depth sensor. So the maximum speed will be constrained by the robot stopping time. Now, based on this intuition regarding exploration behavior, we designed a motion primitive library with 3 different classes of primitives. So first, we have lateral motions and arcs. that bring the robot to its maximum speed. These facilitate both traversal of open space and exploration by navigating parallel to frontiers. So those are. And we also have a set of primitives for forward motion at a lower speed. And these are intended for steady state exploration moving toward frontiers, such as navigating a gap or passage. And finally, the robot can also yaw in place, which can cover a small space very quickly. And if you pay close attention, you should be able to pick out a few of these different kinds of motions and how they're being used in this video below. Now, I've been talking a lot about motion at high speeds, but as we move more quickly, it also becomes harder to avoid collisions. So in my work, we take an invariance-based approach to safe navigation. In this simple form, we can say that if a robot is stopped and not in collision, it will remain safely stopped as such. However, we also want to be able to move around. And the set of states where we're able to safely stop the robot is the backwards reachable set of the set of stop states. And if we have some trajectory or contingency that eventually brings us to a stop, we can execute this trajectory without leaving the safe set. And if we replan, we can extend our time in this backwards reachable set. And if we replan frequently, we can move continuously at high speeds. Now, when we put this all together, view-based exploration, motion primitives, and methods for safe navigation, we have an exploration system that we can deploy on a real robot. So we compared two scenarios, exploring an open space and an environment cluttered with obstacles. And we found that the robot could maintain significantly higher speeds and faster entropy reduction while operating in that open space. And when we tested this planner in open spaces, the robot exhibited rapid spiraling motions, like I have shown before. Again, this is taking advantage of those primitives that move along the frontier. And in the cluttered environment, the robot explored at lower speeds with more varied motions. And we can see in this plot of its position, which is colored according to the different types of primitives it was using. So the robot is able to adapt to the different types of environments it explores in. And on the right, we can see that the robot was able to take advantage of that higher speed to explore the environment more quickly. So it explored about 40% more quickly in open space than the environment with scattered obstacles. So to summarize this section focused on exploration, I started by talking about view-based rewards, and I presented my work contrasting and unifying coverage-based and information-based approaches to exploration. And we saw that simpler coverage-based methods may provide some improvement over more complex information-based approaches. And then I discussed the design of motion primitives for safe exploration at high speeds. And we saw how this led to a sort of spiraling behavior where the robot navigates parallel to the boundary between free and unknown space. Last, this video shows a team of robots exploring a large environment using a distributed planner I developed in my thesis work. And I'll talk a little more about this distributed planning and multi-robot coordination in the next section. So this brings us to the second part of this talk. In this section, I'll present a general and modular algorithm for multi-robot perception planning that operates by sequencing and combining perception planners for individual robots. And specifically, this is a distributed algorithm for submodular maximization that will maintain solution quality for large teams while only slightly weakening approximation guarantees. Now, while I focused on exploration and search and rescue scenarios in the prior part of this talk, I will shift my emphasis to videography for the second part of this talk. But even though the methods I'll be presenting are fairly general. And also, while I started out by talking about active perception methods for individual robots, this section shifts the focus to multi-robot teams. The methods I talk about are complementary. So the techniques I will talk about here in this segment will build on top of the single robot planners to enable coordination of a multi-robot team. Also, this video was taken from work led by Cherie Ho at the AirLab at CMU. And this was from a little before I started on this project. So when I talk about aerial videography, I refer to teams of robots or teams of autonomous flying cameras filming and reconstructing groups of moving agents. And in the future, these systems will be useful for filming team sports, unscripted performances in outdoor environments, or for capturing behaviors of animal groups. And generally, this research direction builds on prevailing interests in drones as filming systems. Today, manual piloted systems, even autonomous systems like the Skydio drone, are increasingly common. However, multi-robot deployment will require significant improvements in autonomy and coordination, and that's something that I'm focusing on in my research. Videography is also special to me because it is a particularly good application for the submodular coordination methods that I study, and I'll go into more detail on that a little bit later. So the algorithm we'll be using for distributed perception planning for videography is the randomized sequential partitions algorithm, or RSP, as I call it. And as an introduction to this approach, RSP is a scalable distributed perception planner for multi-robot teams. And in essence, RSP takes perception planners like what I showed in the last section and extends them efficiently to multi-robot domains. RSP is based on methods for submodular maximization, and it maintains basic optimization guarantees for submodular optimization in expectation. RSP is also applicable to a variety of problems and objective functions, including coverage, target tracking, exploration, and videography. However, we will require some additional assumptions on top of what's typical, and I'll discuss these requirements later. And regarding the analysis, I'll be talking about the key insights are how to remove sequential constraints in the planning process and bounding costs of removing these constraints. So I'll be covering that in the next few slides. Now, stepping back a bit, the optimization problems in my work arise from joint receding horizon perception planning problems for multi-robot teams. And generally, each robot has a space of actions represented by possible motions over the next several seconds. And we'd like the team to maximize some collective utility for their observations or measurements. For example, this utility could be mutual information with respect to target positions or coverage over the environment, like this house. And these utility functions often have useful properties, such as submodularity, which leads me to solve these optimization problems by methods for greedy submodular maximization. So talking about submodularity, I think of submodular optimization as a flexible framework for solving combinatorial sensing and control problems. So in my work, submodular optimization works cleanly with nuanced camera and sensor models, such as with perspective or occlusions. So what is submodularity? In general, submodularity is a widely prevalent functional property of objectives for perception planning and other tasks. And specifically, objectives like coverage are monotonic, which means that with additional observations, or which means they increase with additional observations, and they're submodular, which refers to the property of having diminishing returns. And actually, coverage objectives satisfy additional monotonicity properties, such as the 3 increasing condition, which is the next higher order monotonicity property after submodularity. And I'll discuss the role of this 3 increasing property later in the talk. There's also a large body of work to draw from, studying different kinds of submodular optimization problems. And there are algorithms that obtain approximation guarantees in polynomial time. So that's useful because we'll be solving NP-hard problems. So this brings us back to multi-robot planning. One way to solve receding horizon perception planning problems is by sequential greedy submodular maximization. So with such greedy planners, each robot maximizes the collective perception reward for itself with access to prior robot's decisions. And to do so, each robot will optimize its trajectory via some single robot informative path planner, such as Monte Carlo tree search or some other method. So then the first robot maximizes the reward for itself. The second maximizes the reward conditional on the first robot's decision, and the third conditional on the prior 2 decisions, and so on down the line. And although this approach to multi-robot coordination is quite simple, we do obtain guarantees on solution quality. So specifically, sequential solutions are guaranteed. Oh, I have to play that animation. So sequential solutions are guaranteed to be within at least half of optimal. So what does this mean? For example, if we're trying to optimize trajectories to maximize coverage over the surface of this house, a sequential solution will cover at least half as much of the surface as the optimal set of trajectories. But keep in mind that this is a bound on worst case performance. So in general, we see significantly better results in practice. But a major weakness of this approach is that the planning duration is always at least proportional to the number of robots. Planning durations that increase with the number of robots are a major downside to sequential planning approaches, as this conflicts with our desire to replan frequently while exploring an environment, tracking targets, or filming moving actors. This means that for distributed implementations with reasonably large teams of robots, the accumulation of a few milliseconds of latency for communication at each step could quickly make sequential planning prohibitively time-consuming. So then once we account for the time to solve single robot subproblems, planning fully sequentially quickly becomes intractable if we want to replan frequently. So how do we address this problem of increasing planning time? The RSP algorithm is an efficient approximation of greedy planning that provides a solution to this growth in planning time. When planning via RSP, robots assign themselves randomly to one of n groups, illustrated here with different colors. And the groups of the same color plan in parallel, and the different groups plan in sequence. Thus, we have one sequential step for each of the n robots. So there are a fixed number of steps for any number of robots, instead of one step per robot as for the greedy planners I showed earlier. Now, if we can obtain constant planning time for individual robots, we can also obtain constant planning time for the entire team. To analyze our distributed randomized sequential partition planner, we turn to a graphical model of generalized sequential planning. As I said earlier, when using standard sequential greedy planning, robots have access to all prior decisions in the planning sequence. However, we can also think about what happens when robots have access to only a subset of all prior decisions. In doing so, we can use a directed graph model proposed by Baressafard and Smith, where each directed edge represents access to another robot's decision at planning time. So here I've illustrated the corresponding graph for a standard sequential planner with 6 robots. And this is a complete directed acyclic graph. The edges in this directed graph model of greedy planning also form temporal constraints. A robot cannot begin planning until it has received all of the other robot's decisions will use at planning time. As such, we can design greedy planners where some agents can plan in parallel by deleting edges and thereby allowing robots to ignore some prior decisions. And we can start by partitioning the robots into groups like so, and deleting edges within each group. We can then rearrange the planning steps into a shorter sequence where robots in the same group plan in parallel. However, without additional assumptions over the typical form of the optimization problem, deleting edges and planning in parallel can significantly harm our initial performance guarantee of 1/2. Specifically, we could end up with a suboptimality guarantee that is proportional to 1 over the number of robots planning in parallel. So if we fix the number of sequential steps, we end up with a bound proportional to 1 over the number of robots, which isn't great. So from the perspective of scaling to large numbers of robots, this is a negative result as the approximation guarantee approaches 0 when increasing the size of the team. Moreover, these results also show that no such greedy planners can do better on the standard form of these problems. Instead, I study a slightly more restrictive problem form that's still broadly operable. And in these problems, edges can be associated with fixed costs, which we'll model as edge weights. And we obtain a bound on suboptimality that approaches 1/2 when the cumulative weight of deleted edges is small. And we'll get a bound and expectation for RSP in turn. Further, we can also amortize the cost of removing additional edges from the planner graph on top of the basic RSP algorithm, such as due to unreliable communication or because we want to limit the number of communication hops. And we can model this as another bounded cost. In our analysis of RSP planning, the edge weights in the suboptimality guarantee is a notion of maximum redundancy between robots' observations, as illustrated here, with the intersection of 2 observations for an area coverage reward. The total edge weight is the sum of maximum redundancies across all the pairs of robots. For coverage-like objectives, redundancy decreases monotonically in the presence of prior observations. Here, the effective redundancy between two robots, the area marked by A on the left, decreases due to an observation by the robot shown in red, producing the much smaller area marked B. As such, the initial redundancy between two robots produces an upper bound on the effective redundancy at any time in the planning process. And more generally, this requirement for decreasing redundancy is equivalent to the 3 increasing condition that I mentioned briefly somewhat earlier. And being able to bound the effective redundancy between robots like so is crucial to the analysis of our RSP planners. However, this redundancy is not always so well behaved, such as for some mutual information objectives. Still, we're able to obtain bounds on inter-robot redundancy that are applicable to wide varieties of active perception problems. And subsequently, we're able to provide suboptimality guarantees for RSP that approach the original bound of half. So first, our results are applicable to general sensor coverage problems. And this includes exploration objectives based on expected coverage, like what we discussed earlier. We've also developed a separate bound for target tracking that's specialized to mutual information objectives with independent targets. And at last, our results for RSP are also applicable to videography applications. The details for this are a matter of ongoing work. Now I'd like to show you a few results for planning with RSP. I published a paper in IROS 2021 that focuses on scaling a planner for target tracking up to a large number of robots. The experiments in this paper evaluated scenarios with as many as 96 robots and the same number of targets. In the plot shown here, I compare planners at a slightly smaller scale with as many as 40 robots in order to make the comparison tractable. And here, smaller values are better. And I compare planning with RSP, the black lines, against sequential planning in green, and contrast planners without coordination in blue and orange. The main takeaway here is that performance for RSP quickly approaches that of sequential planning, despite planning with only a few, that is 2 to 8 sequential steps versus 40. And I should also mention that these results are typical, and I've obtained comparable results when evaluating RSP with similar numbers of planning rounds in other application domains. Speedups for RSP can also be quite significant. So with 40 robots, RSP provides a 5 to 20 times speedup compared to planning sequentially. And that speedup gets more significant if we can't reduce the single robot planning to constant time. There's also another side of the story, though. The amount of variation in performance here is really quite small. In this case, we're only talking about a difference of a fraction of a bit of uncertainty. And I'll assert this lack of variation in performance is endemic to problems like target tracking due to implicit coordination that can arise from sharing information, such as observations of target positions. So I think it's worthwhile to look for other domains where planners like RSP can have more significant impacts on system performance. So now, multi-robot aerial videography, if you look at a certain way, essentially comes down to something you might call target coverage. And in this illustration, robots are awarded simply for having robots in view, for example, for having a person in view of a camera. In this case, the robots all have access to ground truth target positions. There's no notion of uncertainty that would otherwise drive implicit coordination. And here, without coordination, robots tend to converge toward the same locations or effectively toward local maxima. So the result is that for videography, coordination has dramatic impacts on system behavior, and it's critical to task performance. And we can see here that coordination is necessary to reliably distributing robots over the targets. Of course, this example is quite simplified. If we want to get further into the problem of planning for videography, we might discretize the person's surface into weighted regions or introduce some other features capturing the quality of the view. And I'll start to add more detail on application of RSP and submodular maximization to videography with the next few slides. I'll register a few more slides left. I see I'm running it low on time. So looking at applying submodular maximization to videography tasks, we started by looking at how robots might film more complex or realistic group behaviors. So here we see a scenario where pairs meet in a center and then swap. And this is supposed to be a challenging task for assignment-based planners, because you might assign robots to film the people of the same color, but then you have to reassign after the group split up. But then since we're just maximizing the view quality directly, our sequential planners are able to handle this swap very smoothly, and the robots are able to cover the actors smoothly through the duration of this task. But so far, this is just looking at coverage. If we want to apply these methods to videography, we might want to develop a more nuanced objective. So there's a few things that we kept in mind. So first, we want to maximize the size of the actors or subjects in the field of view. We want to have diverse views, so see different people or see people from different sides. And generally, we want to have some sort of like uniform coverage over the surface of the actors we're filming. So what we're going to do is we're going to project the subjects into the camera frame and keep track of the number of pixels we'll be seeing on each face. And you can see an example of one of those rendered views. This is actually internal to our planner on the right. And what we do is we uniquely color each of the faces so that we can track how many of the pixels are actually falling on each of the different faces of the targets that we're observing. And what we'll do is we'll sum up the total number of pixels in each face, and we'll take the square root, and this produces what we call the square root pixels per area objective. And that might seem a little abstract, but actually this is monotonic and submodular, so it has all the nice properties we like. And once we go to apply this on a team of robots, it actually works pretty smoothly. So here's one of our first results with that SRPPA objective. And what we see here is that we have a group of people that start out very close together, and the robots are able to film them in formation fairly easily. But as they spread out, the robots shift to focusing more on the actors individually as they can get a little bit closer. So we're able to handle this trade-off as groups form and merge very smoothly. And the last example I'll be showing is these methods easily extend to scenarios that have obstacles or occlusions. So we also implemented a version of this planner based on rendered camera views, and that allowed us to apply sequential planning to very nuanced scenarios like we show here, where we start out with robots filming two targets that are close together, but then they're able to adapt smoothly as they split and then move around an obstacle. So finally, the main takeaways that I'd like to leave you with are first, that submodular maximization is a flexible and modular framework for perception planning and related problems. And second, the RSP is a scalable distributed algorithm for submodular optimization for multi-robot teams. And RSP maintains approximation guarantees approaching the original bound of 1/2. And last, that in the videography and reconstruction problems, we're able to solve challenging problems very well by applying these methods. So now I'd like to say a quick thank you to the people I've collaborated with over the last few years, CMU in RISLab and the AirLab, and then also at JPL. So thank you all for taking the time to listen to me today. I think at this point, we can open it up to questions.
Thank you very much. Very interesting. Anybody wants to start with questions? Don't be shy. Just unmute yourself. Okay, then I will start. Actually, what I noticed, Mika, is that in your work, there was, correct me if I'm wrong, there was very little machine learning involved. Can you comment on that? I mean, in the robotics field, there's lots of people using things like graph neural networks, and I guess reinforcement learning is a bit outdated already, but LLMs and things like that. What do you think about it? What is that something that you wanted to look at in future in your research as well, or?
Yeah, so I think there's a couple of sides to my answer. So one is in my background in the domain, I'm looking a little more at controls. So machine learning and reinforcement learning have, in maybe like the last couple of years, made a little more progress there. But historically, that's one of the like sort of the most challenging areas, because not only do we have to model a system appropriately, but we need to be able to update and respond quickly within like fractions of a second. So I think that's a part of what's led me to think of more of a planning and control type of approach to these problems. But I do want to incorporate more elements of machine learning. In particular, that relates to how environment understanding relates to how we model camera views and think about the perception task. So, for example, there's been a lot of work looking at how predictions for the environment can drive how you explore. So if you understand that, well, this room is going to be so large or empty, maybe we can change our exploration actions based on that. Or machine learning methods like foundation models for segmentation can enable us to develop more nuanced tasks, such as maybe we don't just want to explore an environment, but we want to find a specific object. So that's one of the future directions that I'm looking at. And I've got collaborators up here, so that's the focus of Sungchen's work.
Yeah, I think that, I
And
mean,
yeah,
doing real-time predictions or very fast predictions, that is what machine learning is really good in compared
mhm.
to applying model-based approaches where you need a lot of computational things to get to the same results. So
Yeah. So that's also important to videography. So right now, I assume like uh, scripted motions in my work. And if you start applying that in practice, then you're just looking at the outputs of a Kalman filter, which might be a velocity-based prediction. So incorporating learned models for people's behavior becomes important.
mhm. And the other thing I noticed is that you showed a lot of simulations.
Mhm.
Are you dealing also with like real systems now in at your place, or are you evaluating your methods mainly based on simulations?
Right now, it's mostly simulations. So I've only been at Mines for a few months, so it hasn't really given me much of a chance to ramp up students or purchase and set up equipment. But that's where my work is going next, is scaling up these methods for videography, that I have a sense for how they behave, and starting to apply them on different sorts of mobile robots.
And at least the last question from my side is when I compare RSP to PSO, for example, for perception planning. So we do a little bit of PSO things for
Mhm.
our drones. For exploring visibility over forest. So forest is
Mhm.
mainly random kind of occlusions, and there's so as far as I understand, RSP is that you are splitting your robots into doing tasks that one robot orients itself based on the task that another robot does. So it's a kind of sequential
Mhm.
downstreaming like achievements that one robot did with respect to the tasks that the other robots do. And PSO is a bit different from that in terms of that there is no, there is no direct link between the single drones in terms of improving objectives, except that you are following a leader drone, for example. So
Mhm.
there's maybe a link between like all other drones and one leader drone with a little bit of a bias to a leader, but the rest is more randomized. And in RSP, there is also a random component as far as I understand, but there is still some downstreaming of things from sequentially from drone to drone. Is that correct, or did I
Yeah,
misunderstand it?
yeah. So what I'll emphasize here is there's sort of two different ways that you might imagine dividing up uh, the robots and the partitioning. And the intuitive way might be design groups of robots that are nearby each other, and those all communicate. And that's nice, but it's not what I'm doing. So the in the RSP algorithm, the robots divide themselves up randomly, and the goal with that is actually to get sets of robots that are decoupled. So what we have here is the decoupled robots in the groups, they actually ignore each other's decisions, and then the robots share certain decisions locally through the course of that planning sequence. And the reason that I do that is this allows us to get around any potential challenges related to robots shifting around and the groups changing. And since we're just designing this whole planner structure randomly at each step, we're able to get these results that work well in expectation and have a graph structure that allows robots to take into account the nearby robots' actions implicitly. I think that's maybe a bit of a backwards way of explaining it. But yeah, this approach enables robots that are nearby to share information on what they're doing and to take advantage of that.
Mm-hmm. Okay.
I'm not sure exactly how that relates to the PSO methods that you've used.
I think it's a bit different, but maybe it is an interesting alternative that we can also explore. At the moment, we are not doing that. Do you have any other questions? Anybody online or comments? If that is not the case, then one last question from my side. Looking at using drones for sport events, for recording live sport events. At least in Austria, we had this incident at the Slalom World Cup a couple of years ago where a drone fell off the sky and hit almost the skier. You mentioned a little bit about safety issues, and it seems that in the US, drones are more frequently used for filming sport events. I saw this football match where this was done. But are there any concerns about safety issues here that, I mean, not only about concerns about safety that the drones can hit people, but also are the sports people distracted by drones that are flying very nearby during, a football match? Is that something that is an issue
Yeah.
or?
Um, so I think if I were to comment in a lot of detail on that end up coming down to speculation because I don't really have a good sense of maybe how that all looks on the ground right now. But you do bring up an issue that's really important to me, which is like kind of the human robot interaction side of this problem. So the methods I've talked about right now are like mostly thinking about just like how do you optimize trajectories or plans to view subjects, but it doesn't really take into account like how those actions are being interpreted or understood. So one of the directions that I want to develop now at Minds is collaborating with some of our people at Human Robot Interaction to think about exactly those questions, like how does someone interpret a robot flying nearby them? At what point does the proximity start to maybe change your actions, or do you become comfortable with robots on the field? And then also, is that like situation dependent? So maybe if you're waiting for play to start, a robot hovering nearby is distracting. But if you're in the heat of the moment, say like just about to catch a ball, maybe that distance changes, and you have to take account of both like, well, what are people comfortable with, and then what is safe with respect to the robot's operation. Uh, I do think that some of these challenges related to safety, at least once we get fairly reliable autonomous systems are solvable because, like, for example, with the aerial robots, you have space above the field that you can move into. So there's generally always a safe option to get out of the proximity to the players on the field. And maybe that's a little different from what you see, for example, for autonomous cars, where
Okay. Do you have a question now? Okay, that is not the
Sorry, can you
Okay.
hear me properly? I don't know if my mic is working.
Yeah, we can hear you
I can hear
barely.
you, Patrick.
So I want to maybe add a thing more than a question, not related to American football, but like European football, is if there are drones flying around in the stadium, then there's not also the safety for the players regarding, I don't know, drones falling down, but also the interaction with the fans that came to my mind because there will be people trying to shoot these things if they're flying around, and these obstacles then can injure other people. So maybe there is also another instance of distance regarding fans and they, I don't know, staying out of reach of them. So you know what I mean?
Yeah. Yeah, so I guess how I would handle this is I think about the constraints and then safety requirements in the system on a few different levels. So like one scenario is like the beer bottle. Like someone throws their bottle of beer at the robot, it hits it, and then it crashes. It's not something that is going to happen all the time, but it's something that's going to happen. And in general, like there's a lot of ways that fans can disrupt play. They can also jump out on the field and run in front of the players or something like that. But you stop that because you have police and refs who are responsible for enforcing the rules. And you can kind of handle that a little similarly here. So maybe you build a small enough system that it's not going to harm the players if, say, someone knocks it out of the sky. But maybe in that case, we can accept that our perception quality is going to fail, or there might be a disruption to play if the robot gets knocked out of the sky by one of the people in the audience. But then from the perspective of the drones, also, when that's not happening, we also have to be able to fairly strictly avoid disrupting the play, avoid interfering with all the players, and so on. So there's kind of several levels from like the avoiding the social interactions to avoiding causing harm out of maybe our own planner failures, and then also being able to deal with kind of that unexpected and failing in safe ways. So instead of like a big robot crashing onto the field, maybe we have a small robot that crashes onto the field in the worst case.
The other alternative that you can think of is that you make the drones shoot back.
I suppose so.
Yeah. Okay, so if there is no more question, is there? Then Mika, thank you very much again for this very interesting talk. I think everybody takes a message home here. And for all the students, for the seminar students, the April speaker is not yet confirmed. We will let you know as soon as that is confirmed, but the May speaker is already confirmed. That will be Michael Berish from the University of Utrecht, visualization topic, on the 22nd of May at 2 o'clock. But you will find all the information on Moodle, of course, but not yet the April talk. Yeah, you have to wait a bit for that. Yeah, then thank you very much again for Mika for your talk and for everybody to attend and pay attention here to this. See you next time. And Mika, thank you very much again. Bye-bye.
Thank you. It's all over.
Thank you.
Bye bye.